Good morning, students. Today we will discuss Green's theorem in a plane. This theorem gives the transformation from line integration to surface integration. Here, m and n are continuous functions in x and y and also having continuous derivatives in region R. And here S indicates a closed region in xy plane. Here it is xy plane. The S is the region formed by intersecting any two curves. Suppose I taken it is one curve, suppose like this, y is equal to x square, and taken one more curve, suppose y is equal to x. These two curves are intersecting. You have to form some region. Yes, it is called S, closed region. Now this closed region S is bounded by two curves. It is C1 and one more curve C2. Here S is a closed region in xy plane bounded by a simple closed curve C, and here m and n are continuous functions of x and y and also having continuous derivatives in R. Then Green's theorem give transformation from line integration of m dx plus n dy is equal to surface integration of dou n by dou x minus dou m by dou y with respect to dx dy. Here C is taken in the positive direction. That means the curve is taken in any anti-clockwise direction or clockwise direction. This is called Green's theorem. Now discuss some problems on this Green's theorem. Now solve this problem. Verify Green's theorem for integration of xy plus y square dx plus x square dy, where C is bounded by y is equal to x and y is equal to x square. Here, first we take an xy plane and draw the graphs that the curve. Given curves are given y is equal to x and y is equal to x square. If you taken this curves on the graph like this, it is xy plane, it's y plane. Y is equal to x square represent, suppose like this, y is equal to x square is this graph, it is a parabola, and y is equal to x is the line passing through origin, is passing through origin. Like this, y is equal to x. Now it is the surface S, closed region S. Now this surface is bounded by two curves named as y is equal to x square mode. It is suppose curve C1, and y is equal to x mode. The curve is suppose C2. Like this. It is curve C1. It is curve C2. Now you can wait. Now here in the given question, integration of C xy plus y square dx plus x square dy. If you compare this given statement with the Green's theorem statement, it is nothing but like this, integration of m dx plus n dy. So from this statement you can choose m. What is m here? Where m is equal to xy plus y square and n is equal to x square. You can compare this one. Here it is m, it is n. So here m is equal to xy plus y square, n is equal to x square. Now find the corresponding derivative also by Green's theorem. Dou m by dou y. You can differentiate m only with respect to y terms. While doing y terms, any x terms are there, you can treat constants. Here x is constant, and what is y derivative? 1 plus what is y square derivative? 2y. So dou m by dou y value is how much? X plus 2y. And similarly you can find out dou n by dou x. differentiate n with respect to x terms, only x terms. Here x square derivative is 2x. Next, coming to next one. Now from the graph, the line y is equal to x and y is equal to x square intersect at 2 points. The line y is equal to x and y is equal to x square intersect at O and A from the graph. Intersect at it is some given in the graph already. It is center. It is some point A, 1, 1. That means whenever the graph is here, already it is y is equal to x square and it is y is equal to x line. Now this graph is intersecting at here, center 0, 0. It is some origin and it is the point is 1, 1. That means you can solve these two lines. Y is equal to x and y is equal to x square. You can solve these two lines. Y is remains same. You can equate x is equal to x square and x cancel one time. If x is 1, y also 1. So the coordinates are 0, 0 and 1, 1. That means x is taking value from 0 to 1 and y also taking from value 0 to 1. This is the coordinates. Now you can calculate first when you're solving verifying Green's theorem. Green's theorem statement is circulation of m dx plus n dy is equal to double integration of dou n by dou x minus dou m by dou y with respect to dx dy. Verification means you can prove both LHS and RHS parts must be same. First I am solving LHS part. In LHS part you have circulation of m dx plus n dy. So where the curve is bounded you can calculate here. Here the curve C is bounded by here. See from the graph the curve C is bounded by here along y direction and along AO direction. Here two curves are there. The combination of these two curves will give the complete circulation of the curve C. So I am writing here first along OA direction plus along AO direction. The combination of these two will give the complete value of the total curve C. So I am calculating along OA direction and also AO direction. So m dx plus n dy here. Here also m dx plus n dy. First I am calculating along y direction. Along y direction, already O is the vertex 0, 0 and what is A vertex here 1, 1. So from the graph all of you observed here along y direction the curve is y is equal to x square. The curve is y is equal to x square. That means the total problem we had to convert either x or y. So here from the given curve I am substituting y is equal to x square and find its derivative also. Dy is equal to x square derivative is how much? 2x dx. Now replace these all values in OA direction part. So here along OA m dx plus n dy is equal to along y direction you are selecting y in terms of x. So here you will get x values. X elements you will get x values from 0 to 1. Already m dx plus n dy is already what is m here? M is equal to xy plus y square dx plus x square dy. It is m dx plus n dy. It is m dx plus n dy. it is mdx plus ndy, but in this along y direction, you are replacing y is equal to x square, y is equal to x square, and also dy is equal to 2x dx. You can replace these values. Now the complete integral converts to only x terms. So I taken here x limits from 0 to 1. Now after substituting the above limits here, the problem converts to in place of y substitute x square and dy is equal to 2x dx. Then mdx plus ndy is converts to like this, x into y square, like this, xy plus y square. Y square is already x square whole square, completely x terms plus x square dx. So x square 2x dx. That means I completely convert y in terms of x. Now if you simplify this expression, x is from 0 to 1, it is x cube plus it is x to the power of 4, dx is common, so 2x cube dx, and x from 0 to 1, x cube and 2x cube, we can add 3x cube plus x to the power of 4 with respect to dx. Integrate only x terms, 3 is constant, x cube integration, x power 4 by 4, limits 0 to 1 plus x power 4 integration, x power 5 by 5, limits from 0 to 1. After replacing the limits, okay, you will get up 3 by 4 constant, upper limit in place of x put upper limit 1 power 4 minus 0 plus 1 by 5 is constant, again put upper limit 1, lower limit is 0, you will get 3 by 4 plus 1 by 5, 3 by 4 plus 1 by 5, total it is 19 by 20. It is one curve, it is along y direction. Next, you can do the same thing along AO direction. Along AO direction, now you can take in a anti-clockwise direction. Along AO direction. So A limits are 1, 1 and center is 0, 0. That means when you are taking along this direction here like this, you are taking along this direction. Suppose here, see, it is O, it is A. You are taking this direction along AO. So along AO means this x limits are taking from 1 to 0. And also y is taking from 1 to 0. Okay, now along this AO direction, the curve is y is equal to x. Y is equal to x. Along y is equal to x. So whenever y is equal to x, dy become dx. Now substitute these all values in this line integral along AO direction, mdx plus ndy. Along this direction you can take either x or y, that is along x or y direction you can collect. Here I am taking x values from 1 to 0. Again in mdx plus ndy, in place of y you put x, that is xy. So I am putting x plus y square, x square dx plus x square dx. dy means substitute dx. Now all of you simplify this expression along x from 1 to 0, x square plus x square plus x square with respect to dx. Now totally you have x from 1 to 0, it is total 3x square with respect to dx. 3 is constant and x square integration is x cube by 3, limits from 1 to 0, Now 3 get cancelled. Upper limit is 0 minus lower limit is 1. It is totally minus 1. It is second part. So totally the total integration is given by circulation of this, the total curve m dx plus n dy is nothing but the integration taken along y direction plus along AO direction. So from the first equation, this value is nothing but from the first expression, already we solved this previously here. This value is given by 19 by 20. Now we completed already. And this AO direction value is how much? Minus 1. Simply you can solve minus 1 by 20. It is LHS. That means the complete picture here, see, it is that the total closed curve. Okay, this closed curve. If you take this closed curve, the outer part clearly is how much? Minus 1 by 20 value. It is total curve direction. Okay, it is this along this direction is minus 1 by 20. Now you can show the inner part also minus 1 by 20. Then the Green's theorem is verified. Now coming to the RHS part. Now coming to RHS part of Green's theorem is given by double integration of dou n by dou x minus dou m by dou y with respect dx dy. Here the first integration represents x limits and second it represents y limits. Already in the first we completed dou n by dou x value. So the derivative of dou n by dou x is 2x minus dou m by dou y is x plus 2y with respect to dx dy. Now coming to limits, y limits, y is equal to x square and y is equal to x. It is the curves given. So when you take in double integration, y limits must be in terms of x and x is constant. So y limits are taken from x square to x here down to up x square to x, and x limits are 0 to 1. Already the center is 0, 0. This point is 1, 1. So x is varying from 0 to 1. These are the curves. Now you can solve this in double integration. X is from 0 to 1. Y is equal to x square to x. Simplify this expression. 2x minus x is x minus 2y dx dy. First, we had to solve this double integration. First, you can evaluate first y terms, then you can go to x terms. Whenever x is constant, first you have to evaluate y terms only. So first evaluating y terms. While evaluating y terms, treat x terms are constant. Here x is constant here. Here x is constant, x keep aside. Constant with respect to dy is y minus 2. Again, what is y integration? Y square by 2. And y limits are x square to x. So in this expression, in place of y, you can put these limits, x to x square. And remaining you have dx. Now after replacing the limits, x limits are 0 to 1, x is constant, y means upper limit x minus lower limit is x square, here substituting, minus y upper limit x square minus lower limit x square whole square. With respect to dx. Now simplify this expression, we will get x square minus x cube minus x square plus x to the power of 4 with respect to dx. X square get cancelled. Remaining we have x from 0 to 1, x to the power of 4 minus x cube. Integrate with respect to x now. X to the power of 4 integration x to the power of 5 by 5 minus x cube integration x power 4 by 4 limits 0 to 1. Now replacing upper limit 1 here, 1 by 5, 0 is 0 again, 1 minus 1 by 4. The difference is again minus 1 by 20. It is RHS part. It is RHS part. So from this we conclude that the LHS is minus 1 by 20 and also RHS is minus 1 by 20. Both values are equal. Therefore, hence Green's theorem is verified. Hence, Green's theorem is verified.